Effect of nylon fabric reinforcement on the mechanical performance of adhesive joints made between glass and GFRP. The objective of this research work is to verify the use of the nylon fabric in adhesive joints to investigate the mechanical performance and compare them to similar joints without the addition of the nylon fabric. These aims are investigated by shear tests on single lap and double lap adhesive joints using different combination of adherents and epoxy adhesives, bending tests on GFRP beams with insertion of the nylon fabric in the adhesive joint between GFRP adherents and steel plates according to different geometric combinations. The application area of the present study is the building industry, especially for the innovative building elements such as windows, doors, and curtain walls. For the experimental campaign, a nylon 6 fabric was used. After identifying the appropriate material to increase the stiffness of the joints, experimental mechanical tests were performed after curing under laboratory conditions to test the adhesive joints assembled with epoxy resin. The shear tests were performed on two types of specimens, single-lap adhesive joints between GFRP pultruded adherents and double-lap adhesive joints between GFRP and float glass adherents. 3-point bending tests were also performed on pultruded GFRP beams, with and without nylon and steel reinforcement. The results from the shear tests on the single-lap joints are shown in the load displacement graphs for each configuration tested. To obtain the average stiffness value of the single-lap specimens, since non-linear behavior was found, the graphs of the characteristic curves were divided into two sections to calculate the trend lines. Then the mean value was calculated. The comparison with the obtained results showed the effective contribution of nylon in the joints bonded with epoxy resin, with an increase in stiffness of 54 Newton per millimeter. As for the failure mode of the specimens, it is the light fiber tear failure mode, with the defibration of the GFRP at the bonded interface. Load displacement curves for reinforced and unreinforced configuration for double-lap adhesive joints are shown here. The use of nylon fabric causes a decrease in the ultimate strength for almost all applications. A reduction in the ultimate displacement is observed, accompanied by an increase in the stiffness. The tiered epoxy adhesive offers the best mechanical performance in all configurations with nylon reinforcement. The reduction in ultimate load is due to the interposition of nylon, which has lower strength than the pure adhesive layer. The nylon reinforced configuration in the middle position provides the worst mechanical performance and shows a lower ultimate load value of minus 33% compared to the unreinforced configuration. In general, all reinforced configurations show an increase in stiffness. In particular, the joint configuration with reinforcement on the glass surface leads to a stiffness increase of plus 31%. For the first and second epoxy, a decrease in the ultimate strength values is observed, varying according to the combination tested. Plots give the average load displacement curves for the specimen tested in the 3-point bending tests. The stiffness of the beam reinforced with nylon and steel plates applied with epoxy resin is significantly higher. The bonding with resin is more efficient with respect to the third structural adhesive. Finally, the nylon 6 fabric, in addition to the steel plates, increased the stiffness of the resulting structure by 29% with respect to the unreinforced beams.